Hello, and welcome back to Giving Shapes to Blobs. This is part 2 of our 3-part LMO course. If you haven't seen part 1, you should go back and you should watch those videos and try those exercises because they'll make this week's course, or this week's series of lessons a lot easier, a lot more understandable. So last week we took a look at 3 things. So first of all, we learned what the actual definition of topology is. So a topology is a collection of open sets on a blob, say X. By blob, I just mean set, blob, same word. A topology is a collection of sets, subsets of this blob, or subblobs, which contains the empty set. So the empty set is always an open set. Open sets are the elements of T. And such that if you're given 2 open sets in T, say U and V, then their intersection, denoted with this little cap, is also in T. And thirdly, if we're given a bunch of blobs, here are my weird blob-looking things, and these are all open sets in T, then their union, which is just the points contained in all of these blobs, is also in T. Okay, so actually describing every single open set in a topology sometimes is quite hard. So we also saw the definition of a basis for a topology. So a basis for a topology is a collection of basic open sets. And these always satisfy the following 3 inclusive rules. So the empty set is always a basic open set. Every point is contained in some basic open set. And when you're given 2 basic open sets, here's a basic open set on the left and a basic open set on the right, and any point in the intersection of the 2 basic open sets, here I've got my point P, then there's some basic open set which contains that point and is contained in the intersection. So basis for a topology is a lot easier to describe usually than the topology itself, which you get, by the way, opens just by taking unions. And this always gives a topology, actually, on X. Yeah, basis for a topology was just specifying a basis is often a lot easier than describing the full topology itself. And actually, usually, a basis for a topology kind of contains all of the same information that a topology itself does. We'll see that again and again. Okay, so today we're going to take all of these concepts a little bit further, and we're going to look at some more examples, like I said. Hopefully some strange and fun to think about examples. I'm also going to try to give you some intuition about how to think about weird examples of topologies. But most importantly, when I say think about, I mean compare. So we're going to talk a little bit about how to compare topologies this week. So from the examples, it'd be nice to be able to take the examples we know and actually build new examples out of them. So there are 2 operations. There's the sum and the product. And no, this is not arithmetic, but we will use the same symbols. But we can use sums and products of topological spaces to make new topological spaces. Maybe just a quick note. What do I mean by topological space? So here I just mean a set X, a blob X, with a topology T. So I mean kind of a pair. So a space, so a space is a pair, oops, consisting of a blob or set with a topology on it. And there are lots of these. In fact, they form kind of a zoo, you might say, a whole topological zoo. And Angela's going to take away take it away in the third lesson and actually draw kind of a general sketch of this zoo. It might look something like this. It might look a lot more mathematical. But hopefully it'll help you actually think about topological spaces in the grand scheme of things. Okay, so let's get started with the examples. The first example is kind of a warm-up example I just wanted to give you. It might be something you came up with last week, even on your own. It's called the upper set topology, and you'll see why it's called the upper set topology in a second. The upper set topology on R just consists of all of those sets that start with a number. So maybe call it A. Maybe A is somewhere in between 2 and 3. Maybe it's like right here. Here's A, and extends infinitely in the right direction. So A is this set, or this A infinity is this set right here. So this is an upper set. So all of these are open sets. So for example, 0 infinity is the set which starts at 0 and actually contains all of these numbers over here. You might notice that I chose an A which was actually greater than 0, and so A0 was a subset of this set. Maybe I'll write that up here just to remind you of the notation. Of course, there's another set that we need to throw in here. It's the empty set. And since the whole space itself also has to be an open set, you should notice that actually R, the whole real line, is also an open set. You might have suspected at this point that we actually didn't really need to say that R is also open, because we could have said that these guys are not just the open sets, but are the basic open sets. And so I'm going to erase this thing down here. These are also called upper sets, and they're of the same form. So you notice I didn't erase this, except these left endpoints of the intervals are not real numbers, but instead they're natural numbers. And natural numbers are just, well, these numbers right here, 0, 1, 2, 3, 4, 5, onwards. So, for example, 3 infinity like this in the natural numbers is the set starting with 3. It includes 4, it includes 5, it includes 6, and 7, and 8, and so on and so forth. Maybe kind of a silly observation, but one that will take us to the next example that I wanted to show you, is that for any one of these open sets, any one of these upper sets on the natural numbers, if you look at the complement of that set, so in other words, all the points that are not in this set, so in this case, the complement of 3 to infinity is 0, 1, and 2. This is always a finite set. So I'll say this more generally. The complement of this set right here, A to infinity. So the complement of this set, A to infinity, is the set of numbers which starts at 0, goes to 1, and it continues on until it hits A minus 1, and then it stops. And this is always a finite set. So this actually motivates my next example. What if what we really care about is not the fact that our open sets are actually intervals of this form, but actually just that the complement of every open set is finite. Let's talk about the cofinite topology on the natural numbers. So I had this example for you from before, which was 3 off to infinity like this. So this set, well, its complement, first of all, is 0, 1, 2, which is finite. So this is actually an open set in the cofinite topology. And the open sets in general include, well, 3 to infinity, sure, but actually generally include the intervals of the form a to infinity. But you could also have sets like this. So I could also throw this set into my open set. So this would be the set 1 union and then the right-handed interval, the upper set. So the complement of this is the set 0 and 2, which is a finite set. So this is an open set in this topology. Okay, so let me just describe the sets generally, write it down, and then I'll move on. So actually the open sets in general are the empty set and any subset A of the natural numbers such that the complement of A is finite. Remember, A to the C just means complement. This is all the points that are not in A. Of course, an equivalent way of saying this is that this is the topology on the natural numbers where the closed sets are finite. Okay, so the next example I want to show you is the dictionary topology. The idea behind the dictionary topology, at least the image that you should have in your head when you're trying to imagine how this should go, is of a bookcase, of just a shelf whose books have been arranged alphabetically. There's kind of a whole section of books that are labeled, that begin with an A. Their titles start with an A. And there's another section of the bookcase where the titles start with B, another with C, like this. There's one for E and then one for W. There's also a smaller section of the bookcase where the books start with A, B. So that's these ones right here. There's another section that starts with BO, and that's these two right here. It's the same as B. Here we have CA, and then CO, it's not included, and then E and W. So the idea behind the dictionary topology is to actually consider these sort of intervals of books to be the open sets. The way that you want to think about the dictionary topology in general is that it's a topology on the blob of all words. And by words, I just mean sequences of letters. Like ABC. This is a word for me. The basic open sets are of the form, and I'm going to use D for dictionary, and then you want to write a word down. So here's some word. So this right here is the collection of all words starting with, and then whatever word that you decided to start with. So for example, D of A is the set of all words beginning with A. And if I wanted to make this a little bit more complicated, I could put the word AB in here, since AB is also a word. So all the words starting with AB, kind of like ABC or ABB. These are both words that start with AB. Okay, so let's actually apply this in a slightly more complicated scenario. This set of words is specifically the set of words that are infinite in length. So like this one right here, this is an infinitely long word. And the alphabet for these words is 0, 1. It might be a little weird to think of 0, 1 as an alphabet, but bear with me for a second. So this is one point in the space. It's just the constant 0. The constant 0 sequence. And here's another word right here. So this is a sequence which starts with 0 and then moves on to 1 and then is zeros from here on out. Here I have a word which alternates between 0 and 1. So here is 0, we switch to 1. Okay, well, we're at 1, we're going to switch to 0, and then 1, and then 0, and then 1, and then so on and so forth. These two are a little bit more complicated. I dare you to pause the video and try to figure out actually what the pattern is here, because it's not repeating. And this one on the bottom here is very famous. I'll let you figure that one out. Another way of thinking about actual words of zeros and ones is as paths through this binary tree. So here the idea is you start at the top and you either go left or you go right. And if you go left, then you start your sequence with 0. And if you go right, you add a 1. And if you go right, you add a 1. And if you go left, you write a 0. And of course, these all go on indefinitely. Now down here, I just wanted us to look at the constant 0 sequence. So what path corresponds to the constant 0 sequence? It's this one right here. It's the one where we go 0, 0, 0, 0, and keep doing that. We just choose to go left every single time. Okay, so let's take a look at the alternating sequence. What actual path does this one correspond to? So we start with a 0, and then we do a 1, and then we do a 0, and then we do a 1, and then we're going to keep going on like that. Okay. Now I want to tell you about what 3 of the basic open sets in the dictionary topology for this space look like. Because it's actually very intuitive once you've got this tree picture written out for you. So let's take a look at D of 1. So this is dictionary topology for the word 1. Remember, this is the set of all words that just start with 1. So all the sequences that start with 1. So if we start from the top and we move down along 1, we're right here. This is where we've ended up. And it doesn't matter what we do after that. All of these paths are contained in D of 1. Okay, so you can kind of imagine this open set as being this kind of portion of the tree. And this is where the intuition comes from. Okay, let's do D of 0, 1 now. So here we start at the top, we go down to 0, we travel down to 1, we're right here. Okay, well, all of these paths are the paths that can be found down here in this corner of the tree. And these go on, of course. Okay, let's look at D of 1, 1, 0. So D of 1, 1, 0, we're going to start at the top, go down to 1, we're going to go down to 1, and travel down 0, and we're going to end up here. It's all of these guys in this corner of the tree. You'll notice that this basic open set is actually a subset of this larger one right here. And then, of course, open sets in the dictionary topology are just going to be unions of these. Okay, So we've taken a look at some examples, some pretty interesting examples, especially the cofinite topology and the dictionary topology on the sequences of zeros and ones. Those are very interesting examples, as you'll see in the exercises. How do we actually compare different examples of topologies? So I'll give you one way. This is kind of a weak way of comparing different topologies because it only applies to topologies on the same space. So given topologies T and say T prime on a blob X, we say T is finer than T prime if every open set in T is also open T is finer than T prime if every open set in T prime is also open in T. So all this means is that, well, basically T has more open sets than T prime. And coarser is just the opposite. So T is coarser than T prime if every open set in T is also open in T prime. Now, if T is coarser than T prime, we'll often just write this, and that's actually exactly what this means. Everything in T is also in T prime. So any set open in T is also open in T prime. Okay, so this is a very sort of coarse way to compare topologies, but will come up in the exercises and actually came up earlier during this video. So if you'll go back to the slides with the upper set topology on the natural numbers and the cofinite topology on the natural numbers, you might remember that the cofinite topology is actually a finer topology than the upper set topology on the natural numbers. So that gives you already kind of an interesting example of a way to compare topologies. Okay, so without further ado, go ahead and do those exercises, and I hope to see you back here watching the video for lesson 2.